Hi, this is Kan-Lin speaking. I'm from the National United University Department of Energy Engineering. In the previous section, we talked about the linear scanning voltammetry at a very fast scanning rate and how its outlook, its behavior. In this section, we'll talk about theoretically how they reach this equation or how they derive this equation. If you're interested, actually this can back up to more than 50 years ago. The equation have been derived in 1960s. So over here we talk about the theoretical analysis of linear scanning voltammetry at a fast scanning rate. Over here, if you're interested, actually recommend that if you can get this paper. They're quite comprehensive about the different kind of linear scanning voltammetry. In their paper, they consider many electrochemical reaction and then solve the current as a function of time, those kind of things. Over here, we show basically, for instance, consider reversible reaction. So we had to make the material balance for the O species and R species, and then at the initial condition at time 0, and both the CO at the CO star and the CR at the CR star. That means at the beginning, before the electrochemical reaction taking place, the current voltage change, they always at the initial condition. Maybe the R may be close to 0. If the condition is at the beginning, there's no R species inside the solution. And then the two boundary conditions. One is at X approach to infinity. Then that means in the bulk of the solution is not affected by the electrochemical reaction at the electrode. So however, it maintains original initial condition CO star and then CR close to 0. And at the electrode surface, there's a material balance between the O species and R species, because the O species, the diffusion, for instance, the diffusion of the O is the diffusion from the bulk to the electrode surface, and the electrode surface it generates R. The R will be diffused out, so they had to make a balance over here. And assume it's at the equilibrium, the electrochemical reaction is reversible, is very fast. So the concentration ratio, CO over CR, and this is from the Nernst equation. You may end with this expression. The surface concentration as a function of potential, you may show something like this. And at the time between 0 and the lambda, the potential was scanning from the negative position, and then at the time greater than lambda, then the potential sway back to the other direction. They can do the calculation. Over here, I list two different kind of reaction. One is a reversible charge transfer. The other is irreversible charge transfer. Use a similar government equation and boundary condition. The paper over here they solve. They got the final result. We can compare these two conditions. One, the reaction for the reversible, the O can be reduced into R, and R can be oxidized into O. For irreversible, there's one-way reaction, O only reduced to R, but R cannot be oxidized into O. The potential scan, since it can be reversible, so actually we can scan back the potential. And the other one for irreversible reaction is just scanning from one direction. And then the government equation over here, since it's reversible, so we had to consider the balance, material balance of the R species. But over here, the irreversible, we only consider one O species here. And then the boundary condition or the initial condition, they are almost the same. The only difference is over here at the electrode surface. At the electrode surface over here, we had to make a flux balance for the O and R. And then the concentration gradient Nernst equation here. But at the electrode surface for irreversible reaction, the diffusion rate equal to electrokinetic reaction, the kinetic, like a Tafel equation, and then the K over here equal to something like this, and then B is, and then this scanning rate, potential voltage scanning rate here, the V here. So there's the difference is at the boundary condition. So with this paper, actually solve at a different scenario and come out with a final result. If you're interested, you can read that paper. This one. Over here, I just compared those two reversible and irreversible. For the reversible condition, the current can be eventually can be solved like this, and then this is scanning rate, the scanning rate times the t. So actually, scanning rate times the t give you the electric potential as a function of time here, and also here it's scanning as a function of time here. So we can, from this one, we can plot this one as a function of potential. So this will come this result for this, and then the sigma is actually is a electric potential here. So we plot E minus E half the while we can get this relationship, and then the E peak, and then this the I peak, and then at the 1/2 of the I peak, then there's the E peak and half potential. These two potential have a unique situation over here, the I peak and the E peak minus E peak over here, E peak and half. And then they have this unique situation. So if you're scanning, the I peak at a different scanning rate is a linear proportion to the V mu 1/2. So they should be supposed to be linear proportion to this scanning rate. You get a fast scanning rate, you get a higher peak potential. And then if you plot the I peak against this one, then the slope will be, you got this slope here. So this is numerical data they list on the paper, and if you're interested, actually you can trace back original paper. And from here, if you get a different scanning rate, then you can see the peak current at a different scan rate will be increased. But it's a reversible reaction. The reaction rate is very fast. So even you're scanning at a much fast, increase the scanning rate, the peak potential, E peak, also always remain the same. That means that electron reaction is so fast, they didn't see any change in scanning rate will be affect the final profile. On the other side, if for the irreversible reaction, you can see the slightly different is the peak is since not so symmetric over here. The detail of the peak potential still is a function of the scanning rate, but the parameter slightly different here. And now if this numerical data just for the reference. And if you plot at a different scanning rate, you might see the difference is actually the peak potential. It depends on potential on the potential scanning rate here, because at highest scanning rate, it seems the reaction cannot catch up the scanning rate, so the potential kind of shift toward a more negative direction over here, and the current is a little bit smaller than at a reversible condition because reaction much faster. So in a reversible reaction, the peak potential is independent of scanning rate, but for irreversible reaction, the peak potential is a function of scanning rate. You can see is keep changing at a different scanning rate. And the peak and peak half actually is not. They're still the same. To compare this one for reversible reaction and the irreversible reaction, you can see for irreversible reaction, it's slightly unsymmetric. All the parameters are keep the same, but we compare the reversible in reversible reaction. they kind of similar behavior. But since it looks like if you scan the same potential range, this epic seems in the middle, but the irreversible seems unsymmetric, something like that.